So what I will present is the design of B1 ground improvement. So that's basically this here, so the inclusions, but inclusions without unconfined compressive strength. I will try to do this along a very simple example, but before we come to the example, we have to dig in the code and find the bits and pieces we need for our design. So basically, which design situations we have to consider, which geometrical properties, what's the zone of influence, where do we find actions and environmental influences, and also where we find actions, permanent and variable, and what to do with them. This is scattered a little bit. I try to put this all together here in this list. When we do design, of course, we do the design inside a geotechnical design model. And there are, of course, requirements for this geotechnical design model. So this design model needs to cover certain aspects of the behavior of the system. And in this clause here in the code, you will find some requirements for this, and those are important. So number one is it should consider all these interaction effects between ground and inclusion. So it's not that we just take some average value and smear everything around. We need to look at it more accurately. Then of course, if we do that, then comes number two, and that means we need to determine in our approach what ratio of the load is supported by the inclusion and what ratio is supported by the ground. This of course includes number three, so this cannot be done without considering the stiffness ratio. And another requirement or allowance in this case is you can do the analysis based on numerical modeling. This is something I will not do in my example, because then of course we would completely jump out of clause 12. We would go into clause 1 and all the rules and regulations for numerical calculations. And there are also rules to verify SLS and ULS with numerical models. So this is something I will not present. I will stay with analytical methods here. And then of course the next question is, in my model, what kind of verifications are required? Well, number one, I need to determine the properties of the inclusion, in brackets also the ground around it. Verify ULS of the system using separate ground and inclusion properties. That's a bit tricky in analytical methods, but I will show how this can be done. Verify ULS in general for the system. Then there is a clause, you should also look at compression and shear resistance in inclusions and the ground. How this can be done, I will show, or what this means. And sometimes stone columns are also geotextile enclosed, and in those cases there would be additional verifications. In my example, I have not done this because the majority of stone columns have no geotextile enclosure, and therefore I'm not covering this here. Well, first of all, we need a design model. One design model that is extensively used and has been described in literature and checked and verified many times over is the Priebe method. So what does this method basically mean? It means that we have a unit cell, and in this unit cell we have the distinction here between the soil and the column. And because it's usually not one single column, it's many columns, that means that we have certain conditions. There is a bit of symmetry. We have at the border of the unit cell certain conditions, for example, no horizontal deformation. Well, just for the sake of completeness, I have put in here all the equations which are part of this design approach that was proposed by Mr. Priebe. What is important to know is that in this design approach, a lot is happening horizontally in the system, because the column is reliant upon the lateral support of the surrounding ground. So basically all these calculations start with basically when the column it's loaded, it's basically leaning into the surrounding ground. The surrounding ground is supporting it, and based on that you can derive those formulas and come basically to a calculation of a so-called improvement factor. And this improvement factor is basically a stress relief factor. And that exactly allows us to do what the code requires, calculating the share of load that is supported by the column and the share of load that is supported by the surrounding ground. This is done, of course, in certain steps. This is the basic factor of improvement. In this, there is still an assumption. This assumption needs to be corrected. What means corrected? Corrected means basically that an initial assumption is that the column is incompressible, and that's not the case. So basically, if I replace the soil completely by stone column material, then the maximum achievable improvement ratio is stiffness ratio of the original ground, stiffness ratio of the column. So what correction do I need? I calculate basically the area ratio, where I get exactly the improvement ratio of the stiffness ratios, and with that I basically shift all my curves and I correct this and have now an improvement factor. I can go a bit further on because of course with depth the lateral support of the column increases, so also for that there are formulas, so the improvement gets better with depth. And as I said, the improvement ratio is a stress relief factor for the ground. So I have all the figures in hand, so I can calculate exactly the load distribution. And well, because the column is much stiffer than the ground, they over proportionally support load. So that means the column supports more load than corresponds to its area ratio. And it has been found basically that it's justified to weigh the load ratio according or to when you calculate shear parameters for the new composite system, basically, that you can do that along the load ratios with some distinctions for cohesion. Well, the system is as such a full displacement system. Trying to get this here running. So full displacement basically means we are shifting the ground, we are pushing it aside. Part of the installation is also that we activate the column. So basically the tool is moving in pilgrim steps, so we lift it and then we push it. So basically in our material we are definitely not in primary loading, we are in reloading most of the time, and we are exposing the surrounding ground to vibration, which for certain grounds, not for all grounds, can result in a densification. And if those effects are verifiable and quantifiable, then there is no reason not to consider that in our design calculations. So you could definitely include those installation effects as favorable effects when you consider the improvement ratio. So now let's go a little bit closer to a very simple example how this can be done. Well, first of all, we need to come to our design loads. If we go into Eurocode 0, this provides a number of equations which allow us to do this. I have here opted to use the first equation here. This equation actually is very similar to what we are using in the current generation of Eurocodes. And therefore I'm using this just to show that we are talking about an evolution, not a revolution of design. Then we need to factor those loads. Eurocode 0 provides various options how this can be done. I find it, or when I first saw this table, it was a little bit confusing because you see this last column, geotechnical design, and that's verification case 3 and 4. But on the other hand, if you read the footnote, then you see verification case 1, and that is both used for structural and geotechnical design. So basically, this formula, which is very close to what we are doing today, is something that is very familiar to us. Then, and that is new, is this concept of consequence classes. So those consequence classes can be used to basically determine how important a certain structure is, or basically what are the effects if this fails, and there is definitely some difference if this is a very important public infrastructure, or if this is a remote rural agricultural facility where for many days and weeks nobody sets foot into. Most of our structures would definitely fall into this category, so KF 1.0, and so that was the action side. We are looking now at the resistance side, and I have opted in my example to use the resistance factor approach. There is extensive discussion what is better, resistance factor, material factor approach. I've chosen this resistance factor approach because I can use then the representative parameters for the ground, and that gives me the more realistic or expected failure mechanisms, or the geometry of the failure mechanisms are probably nearer to what I can expect. But of course, material factor can also be used for that. If I'm using the resistance factor approach, then as I said, I'm opting for verification case 1, and that means I'm not factoring ground properties, I'm factoring resistances. And if you look carefully here, 1.4, for example, for bearing resistance, and you remember what Carolina just presented, so that's also 1.4. If you remember the piling session from today in the morning, that was also something with 1.4. So basically we are talking about a very consistent safety level in piling and ground improvement. So the idea behind this is basically that the level of safety, whether you do piling, rigid inclusions, or any other form of ground improvement, should be the same. If I'm going for the resistance factor approach, then I'm not factoring my material properties. So basically I'm using M1, and M1 means everything remains on the representative level. Now coming to my example, a very simple one, maybe a bit textbook-like. So that means I have a single footing, 3 meters by 5 meters in size. I've put a number of B1 inclusions under it. It's loaded in total by 2,500 kilonewtons. How that is split, I will come to that in a minute. I have soil properties. Those are basically representative values. I'm not delving into where I get them from. Let's assume I have a geotechnical report about the soil investigation, and those representative values have been given in that report. I have column properties. The behavior of stone columns is governed basically both by its stiffness parameters and also by its shear parameters. You see here very high friction angles of 4 to 7.5 degrees and a very high stiffness modulus. The reason is for the stiffness modulus, as I explained already, the columns are highly compacted. They are also activated, so that means the full weight of the rig is used to load them during execution. And the friction angle is also something which we have extensively tested. So if you use this much compaction energy on this type of material, then you get not just very high stiffness, you also get very high shear parameters. And those shear parameters have been tested. So we have extracted material from columns by replacement methods. We have replicated this relative density in the lab, and reality found friction angles in excess of 50 degrees. So basically this is a realistic value for this kind of material. So now let's start a few computations. So my design load, the permanent load, self-weight is 1,500 kilonewtons. Live load is 1,000. Consequence class was 2. So that means my consequence class factor is 1.0. And if I'm adding everything up and multiplying it with all the relevant factors, then I'm coming to a design load of 3,525 kilonewtons. As I said, I'm using resistance factor approach, so not factoring materials. So I only look at the overall system resistance, and that needs to be then divided by the partial safety factor of 1.4. This calculation is done in layers. Well, we have one relevant geotechnical unit here, but also in the calculation this is done layer-wise. And then we get this improvement with depth. So you see here substantial improvements. You also see it basically in the last column here over there, that the improvement is increasing with depth if I consider this. But for my failure calculations, I stay here with this values here. And that, in the end, provides me with this set of new friction parameters and stiffness parameters for this treated zone under the footing. In my calculation, I can then, it's a few smaller prints here, but I can basically calculate the column force and the residual stress in the soil, and that's exactly what the code requires me to do. I can, and that is SLS, I can say what is the settlement if I do nothing, what is the settlement if I have the stone columns. So you see here very clearly the reduction. For ULS, I'm using the N2 values, so I'm considering everything regarding the stiffness. Then there is this clause about verifying shear resistance in inclusions and the ground. If you take these formulas which have been proposed, well, you have the column that would start somehow to lean into the ground, so the column is moving. So what kind of earth pressure do I have in the column? The maximum, once it really starts moving, would be the active earth pressure. The ground, well, even without considering the installation effects, would provide earth resistance. So I have, if the column is really deforming, the active earth pressure. You know, if I compare this earth pressure here to the horizontal resistance, then I see I have plenty of safety, at least much more than this 1.4. And even if I'm then going back into the column, so I have the load on the column, I have the maximum lateral support from the soil, and that would allow the column then to support more than 1,000 kilonewtons per square meter, and that is much more than the 650 kilonewtons that the column in fact has, so I get also a very high safety against this. I say here optional because this is literally always the case, so basically this type of failure in practice does not really occur. Then of course we need, in a last step, to verify the system resistance, so that's basically base failure. And now we have a bit of a problem. So we have a zone under the footing, and this zone has been improved. And we have a zone next to the footing, and this zone has not been improved. If we take the typical failure mechanisms from literature, then of course we get one problem. If we build the geometry of this failure mechanism under the footing and next to the footing, then I get an inconsistency. I have no smooth transition. So this is something I need to consider. After many studies, it has been found that modifying this in a way that you calculate a virtual width of the single footing, so that I I have again a transition, another discontinuity in my failure mechanism. I get a new virtual width of the foundation, and then I can use this virtual width and do my base failure verification, but of course with the original soil parameters in this case. So basically I have done all my calculations, verifications in B1. I have calculated for this zone, for this composite system, a new set of parameters. And in the verification equation for B1 inclusions, I need to verify the overall system resistance without looking at the ground and the inclusions individually. So that means even the code basically pushes me from B1 to A1 for this specific verification. In this equation, well, the safety factor is 1.4, the model factor is 1.0 per definition. Well, I use this new virtual width in my calculation, and I come to a utilization factor here. It's this small figure, 0.558. So basically the base failure with stone columns present is given. Just for comparison, if I would do the same calculation in this type of soil without any improvement, then I would find I'm slightly above the utilization, slightly above 1.0. So the foundation pressure is larger than the resistance, and that would not work. And this is basically the way how to do those verifications. A few words about testing. That's part of what we call implementation of design. So there are some control tests mentioned in the code. One is field testing inside or in between inclusions. So basically you can do CPTs in the inclusions, in between the inclusions. That's okay. Then, and that is also very informative, you can do zone load test or dummy footing test. The key is that this does not just load the column as such, it loads the column and the surrounding ground. So basically that is close to the real situation you have afterwards. And then what is also done very often, and this is explicitly not named in Eurocode 7, are the plate load tests. So basically you take a plate load test, you load just the column. The result is very often that you produce a small scale failure close to the surface, and that tells you exactly nothing, because this has nothing to do with the final load situation. Yeah, so that is our idea how to do the verification of B1 rigid inclusions, or B1 inclusions, not rigid inclusions, using the new Eurocode. Thank you.